In this example, we'll have a look at a couple of methods or forms in which we can simplify a Boolean expression using a Carnot map. And the most common form of simplification, which we'll look at first, is what is known as the sum of products, or minimal additive form. But we'll also then look at an alternative way of writing it as a product of sums, or minimal multiplicative form. So, starting with our sum of products form, let's look at this in relation to the expression shown here. F equals W bar X bar Y plus Z bar X bar Y plus Y bar Z bar. And there are four variables in this expression, W, X, Y, Z. So here is an example of how we could set up a Carnot map with those four variables in it. Noticing that one of them being in the right hand side two squares here, or two columns, then the one opposite it is in the middle two columns. And the same here. One of them is in the bottom two rows, so the other one is in the middle two rows. And that's to ensure we get every combination of states. So then we look at each of the terms in turn and put ones for where these are satisfied. So W bar and X bar and Y. Now the W bar and Y column will be this one here, and if we also want it to be an X bar, that will be the first two rows of that column only. So I'll put ones there. The next one, Z bar and X bar and Y. So looking at that, Z bar and X bar is going to be the top row, and we also require this to be in Y, so that is only going to be these two. The last one, Y bar and Z bar. Now Y bar is the first and last column. Z bar is the first and last row. So that's actually just going to be the four corners here that are both in that column and in that row. Everything else is going to be zeros. And we then look for 8 squares, 4 squares, 2 squares, 1 squares of ones, where we try to cover it with as few squares that are as large as possible. Now there are no 8 squares of ones, but there are a couple of 4 squares. In particular, remembering that a 4 square can be across a row, this here, for instance, is a 4 square of ones. Now a 4 square can also occur in the corners of the Carnot map, and here all 4 corners are in fact the same, they're all ones, so that is another 4 square. And that's all the 4 squares we could cover this with, but now we can see here that there is a 2 square of ones here, and altogether that now has covered all of our ones, so that we can now write down our simplified sum of products expression. First looking at the red 4 square that we circled, which was across the first row here. What is that first row? Well, all of that first row is in Z bar, and all of that first row is also in X bar. So therefore that row is going to be written as Z bar X bar. Look at our other 4 square that was in green in the corners. That one there we already saw was always in Z bar and also always in Y bar. So that one there is Y bar and Z bar. And finally, looking at our blue 2 square, that one there is always in the Y column, it's also always in the W bar column, and it's always in the X bar row. So therefore this would be our simplified expression in sum of products form. So let's now have a look at how we could simplify the expression we started with as a product of sums. And we can actually look back at the Carnot map we constructed in the first part where we were getting a sum of products. And there, to get the sum of products, we started off by selecting large squares of ones. The main difference is when we're doing a product of sums, we start off by selecting as big squares as possible of zeros. So let's look, there's no 8 squares again, but are there any 4 squares? And what is the smallest number of such squares we could use to cover this? And we can see, for instance, that there is a 4 square down here, which I'll circle in red. There is another 4 square over here, which I'll circle in green. And here we need to be careful because there's that row of zeros, but that might end up overlapping with everything else. The most efficient way now would actually be to look at these together, which I'll circle in yellow. Those two zeros with those two zeros on the other side there also make up a 4 square. And by doing this, we've now covered all of the zeros. So that, for instance, we wouldn't want to use the third row as another 4 square because that would just be making it unnecessarily complicated. So we now use the zeros to write an expression. But what do the zeros show? They don't show f, they actually show the negation of f, or f bar, the circuit that's open when f is closed and closed when f is open. So therefore it's actually f bar that we will be writing down from our zeros. And what is it? Well, looking at the red 4 square, that is in the column for y and in the rows for x. So that red 4 square is x and y. Looking at the green 4 square, that is in the column for w and in the row for z, so that's wz. And lastly, looking at our yellow 4 square that we saw over the edges there, that one is in y bar always, and it is also always in z. So this is the expression for the negation of our circuit, f bar, which means that the actual circuit f that we're interested in will be all of this with a bar over the top. And so to get the product of sums form, we then simplify this expression using De Morgan's laws. And the first of De Morgan's laws that is useful to us says that a plus b bar is equal to a bar b bar. So that will help us here, because breaking it up in these blocks, we can see that f is in fact equal to xy bar times wz bar times y bar z, or with a bar on it. The second De Morgan law is also useful. That allows us to simplify these blocks further by saying that AB, or with a bar on it, is A bar plus B bar. And so now, for instance, the first part, xy with a bar on it, becomes x bar plus y bar. The next part, wz bar, becomes w bar plus z bar. And the last bit here, y bar z, becomes y bar bar, which is just y, plus z bar. And this is what is known as the product of sums form, or the minimal multiplicative form of our expression. So there we've found two ways of simplifying a Boolean expression.